we are back at AP Review. This is 2019 BC Free Response 2, which is a calculator problem. It is polar. All right, so we're given a polar curve. It's much nicer on the real AP. This is my terrible version. They define it as r of theta equals 3 square root of theta, sine of theta squared, the theta squared, not the sine, for 0 to root square root of pi. So that's shown in this figure here. So first thing we're asked to do is find the area of S, right? Really, this is testing if you memorize the formula for the area of a polar curve and if you know how to use your calculator. So the area of a polar curve is 1/2 the integral from the start to the end, which they conveniently gave to us as 0 to root pi. This is not a curve that loops multiple times, of r of theta quantity squared. So it's really, with respect to theta, obviously, it's really common that you're either going to forget the 1/2 or the r squared. You're going to remember the r, but not the squared. I have another video earlier on why this is the area of polar curves, and you can definitely go back and look at it if that helps you to memorize it. The funny thing is, even if you do that, you're sometimes going to forget one of these two things when you type it in your calculator. I say that as someone who literally just forgot the squared when I typed it in my calculator and had to go back and fix it. So just be really meticulous about what you put in your calculator. When you type this in your calculator, you're going to end up getting a 3.534 as your answer. So this is all the AP needs to see from you. But it's really important that you know how to enter this in your calculator. So I'm going to do a quick revisit on that. So you're going to type into your calculator 0.5, math 9, which is function integrate, r1 squared, again, that's the thing that I always mysteriously forget if I'm not careful, with respect to theta from 0 to the square root of pi, right? And that's going to spit out this answer. Again, the AP doesn't want to see this notation, but if you don't know how to type it in, then the AP is absolutely going to get you because you won't be able to get the information you need. So it's 0.5, right? I go to math 9, and I pick function integrate, right? I go to vars. I go to yvars because yvars stands for outputs, even though it's obviously an r, not a y, and I pick r1, and then I square it, which is the thing that my brain always forgets on an AP. And then I put 0 to the square root of pi, and then I hit enter, and it should give me my answer. Cool. All right, next bit, part B. Sorry, I wrecked my graph. All right, part B. What is the average distance from the origin of a point on the polar curve, that r of theta we already have, for 0 to square root of pi? Cool. So r is actually the distance from the origin. That's how this is defined, right? You don't need like a distance formula. That's what it is. Distance from origin. That's how you do polar coordinates, right? Theta is the direction and r is how far you are from the origin. It's a directed distance. So all you need to do is use the average value of a function formula, which when you want to find an average value of a function, you integrate from the start to end of the function, and you divide by the width of the integral. So we usually do that by doing 1 over end minus start, right? And again, that's all the AP needs to see from you, and then type, and they want an answer. So it's going to end up being a 1.579 or 80, depending on how you round or truncate, right? Either of those would be fine. This is all the AP wants to see, right? But again, you need to make sure that you know how to enter this in your calculator. So I'm going to make sure that I put 1 divided by square root of parentheses pi, right? And then math 9, which is my function integrate, r sub 1, make sure it's not squared anymore, with respect to theta from 0 to the square root of pi. Now, a little bit of advice here. If I were you, you already typed this in your calculator just with this as a 0.5 instead, right? So if I were you, well, and with no squared here, obviously. So if I were you, I might be a lazy bum and just hit second enter and then pulls up all the stuff. I would change this into a 1 divided by, second insert, divided by square root of pi, right? Oh, I lost my math 9. Hang on. All right. I didn't mean function. I meant polar. There we go. All right. So I inserted instead of deleting, and I ended up with my ridiculous coefficient in front of a function integrate. I changed my r sub 1 quantity squared to just an r sub 1, and that should give me my answer. We'll see. I kind of messed it up a little, but it should be all right. Yep, there's my answer. Cool. All right, I totally butchered the graph, so I'm redrawing it sort of-ish for part C. All right, so Here's our graph. In part C, there is a line through the origin with a positive slope m that divides the region S into two regions with equal areas, right? But do not solve an equation involving one or more integrals whose solution gives the value of m. So what they're saying is, starting at the origin, there's some line with the positive slope, right? We'll just call it line L, that has a slope such that the rise over run, right, the slope of this thing is m, right? And that this divides the region into two equal portions, right, of area. So the trick is that we need to find this angle that I'm going to call alpha, because that's going to be the bound, right? Essentially what's happening is if I integrate from 0 to alpha, I get this area, and if I integrate from alpha to root pi, I get the other area, and they should be equal. Or I could say that if I integrate from 0 to alpha, it should be half of the integral we got in part A. That's also fine. There's a bunch of ways to do it. So the wild card in this problem is figuring out a way to express alpha in terms of m, right? So here's what I know. I know that the slope of this thing, right, is m over 1, right? So if you were to look at, so whatever this y-coordinate is and whatever this x-coordinate is, right, of this point right here that's on the curve, I know that the slope of this thing has to essentially be y over x, because the other point is 0, 0, and this point is some xy in Cartesian coordinates, right? So the slope of this thing has to be y on top of x. Well, using SOHCAHTOA, that's the same as the tangent of this mystery alpha bound. So tangent inverse of m must be my alpha. This is the mystery bound. So there are a couple different ways to do this, right? One way to do this is to say the 1/2 equals the other half. So 1/2 the integral from 0 to the inverse tangent of m of r of theta quantity squared, right? First half equals the second half. Oh, sorry, it's a d theta. My brain is tragic. 1/2 the integral from the inverse tangent of m to root pi, which was the other bound, is the r of theta quantity squared with respect to theta, right, is the integral of that. That's fine, right? That's one way to do it. Half equals the other half. The other way you might see it is the first half, right? So this is the first half of this thing, right? This is the half from 0 to alpha, the thing I called alpha. Of theta quantity squared with respect to theta. You could say, oh, that's 1/2 of the thing you wrote in part A, right? The total area in part A, which was 1/2 the integral from 0 to root pi of r of theta quantity squared. Sorry, there's a lot of layers to these things, right? That's another way to write it. You also could have, instead of doing the first half, you could have done the second half, which would have been the inverse tangent of m up to root pi. That's fine. Any of them are fine. Based on the specifications they gave you, they had to be integral expressions, and they had to involve m in some way, like in terms of m. So that's it. That's what you need. All right, cool. Part D. For k is greater than 0, let a of k be the area of the portion of the region S that is also inside the circle k cosine theta. Find the limit as k approaches infinity of a of k. Cool. So let's draw an image of this thing. Okay, so for D, right, and I'm going to redraw my terrible graph again. Looks kind of like this. Okay, so the circle A of k, right? So the circle we have is R equals k cosine theta, right? So when you draw this, right, if you were to picture what this curve is going to look like, k cosine theta, right, when theta is 0, the r value would be k, right? So it'd be start out somewhere here at k, right? And then when theta is pi over 2, which would be here, you'd be back at 0, right? And then what would happen anywhere after pi over 2 for a little bit is that you would get, when you're over here, you'd get negative k's, so they'd essentially loop back to the positive side, right? So anywhere that you're in this quadrant is actually sending you over here, right? So what's going to end up happening is you're looking at a graph that looks kind of like this, right? So the trick here is that you want the area in this window right here. So what I want you to notice is that window starts at 0, right? And ended when this thing hit back here at pi over 2, right? So the bounds on this thing are 0 to pi over 2. So this area, right? And so what's going to happen is that this thing is the area inside, right? This is the area inside the r value from close all points to the right. So as this radius gets bigger, it's going to look more and more like this, right? So it's essentially going to keep, as k gets bigger, what's eventually going to happen is this thing is going to enclose everything up until the x-axis. So essentially, the limit as k approaches infinity, because you can see if k were a small number, it would look like this, and then it looks like this, and then as k gets bigger, it looks like this, and then as k gets bigger, it looks like this. Eventually, it's going to be this whole area. The limit as k approaches infinity of this thing is essentially just this chunk of the area, meaning the 1/2 the integral from 0 to pi over 2 of r of theta quantity squared with respect to theta, right? Now, one way to see this, because it can be a little bit hard to see, and I sort of was, I sort of made up a circle and did it in my head with an arbitrary k, and then I had to picture what happens as k gets bigger, and as k gets bigger, it's going to come out to where the new k is, and k is big, and k is bigger. Another way to do this is to pick a couple different k's in your calculator, and by visual inspection, you would see very quickly that as k gets really big, this ends up essentially being the entire area. So we end up integrating from 0 to pi over 2 of this r of theta quantity squared, which you could then type into your calculator. In fact, you've already done that just with a root pi. You could easily change the root pi into a pi over 2, and when you do that, you get a 3.324. So again, that's totally a tricky question. Most of these questions have something a little bit tricky at the end.